Okay, now let's take a look at forces tutorial. Question 12. A part 2. Okay, you are given a beaker of water. Okay, the weight of this beaker of water with water all the way to the brim, right? You are told that is 100 Newton. So that is the weight of the water. Let's call it W. Then they are going to introduce a ball by applying a force to the ball to push it down. Okay, you are asked what is the amount of water that overflow in part 1. So that one we get the answer to be 31.4. So this is, let's call it W prime, which is the weight of water overflow. Okay, then you are asked to find what will be the reading on the scale now with the ball pushed in as shown in the diagram. So let's draw a scale here. In order to know what is the reading adding on the scale, we need to know what are the forces acting on the scale. So let's consider free body diagram of the ball. When you say draw free body diagram, that means you only consider forces acting on that body. Okay, so I'm going to consider free body diagram of ball. That means I'm only looking at forces acting on the ball. So what I will have will be the pull of the gravity on the ball, which is the weight of the ball. I'm going to call it W with a subscript B, which is the weight of the ball. Then I also have a downward push by the external agent. Okay, so it could be a person pushing down the ball. And because the ball is in the water will exert an upward force called U. Okay, so this is the force by water on ball. So we have 3 forces acting on the ball, and because the ball is in equilibrium, so we expect the total upward force to be equal to that of downward force. So the upthrust, which is equals to the force by water on ball, it will be equals to the applied force plus the weight of the ball. Okay, so that is for the ball, and it does not give us the reading on the scale because the ball is not in contact with the scale. So what we need to consider, and what is more important to consider, will be the container of the water. So let's consider forces acting on the container of the water. So we are going to draw the free body diagram for the container of the water. Okay, the ball is here, but now we're not going to consider it. We will just look at forces acting on the water. When I say I'm not going to consider the ball, that means I'm not going to consider forces acting on the ball. I'm only looking at forces acting on the water. So the first forces acting on the water will be the weight of the water that remain. So initially you're told that this is 100 Newton. Okay, without the ball. With the ball, now the weight will be 100. Okay, I'm going to call this W prime. The weight of the remaining water will be the 100 Newton minus the amount that overflow. So that will give me the weight of the water remaining. Then because there is a force by water on ball, by Newton's third law, there must be a force by ball on water. Okay, and this force you can call it a down thrust. So from here we know that the up thrust equals to down thrust from Newton's third law. And how do we find this up thrust, which is equals to down thrust? Okay, we make use of the concept for up thrust. We know that up thrust equals to rho Vg. Okay, so up thrust is equals to down thrust equals to rho, which is the density of the water, V the volume of the object times G. And this we have previously calculated in A part 1. This is 31.4. So to find the reading on the scale, okay, the scale is here, right? There will be an upward force, which is the normal reaction force. Again, a container of water is in equilibrium, so N equals to W prime plus D, or D plus W prime. So in this case, my D is 31.4, which is numerically equals to the upthrust, Newton, and then plus W, which is 100 minus 31.4. So the reading on the scale will still be 100 Newton.